Assalamu alaikum dear students. This is our next problem having been chosen from the same book, that is Modern Physics by Paul A. Tipler. As usual, we first come to its statement. Okay, the orbital speed of the sun relative to the center of the Milky Way is about 250 kilometer per second. 250 kilometer meaning 25 with 4 zeros meter per second. Okay, by what fraction do the relativistic and Newtonian values differ? For part A, the sun's momentum and the sun's kinetic energy. Okay, so dear students, we have to find momentum and kinetic energy both in Newtonian or classical mechanics and in relativity. Okay, so first we develop a foundation regarding the solution of this problem. Okay, here are some snapshots which will help us in solving this problem. Okay, these snapshots have been chosen from different books. Dear students, these first two snapshots which are in yellow color are from University Physics Young Friedman. However, about remaining snapshots, I am not very much clear. Okay, but I think these snapshots have been taken from Physics for Scientists and Engineers by Gianni Mosca, etc. Okay, anyhow, first snapshot is about Lorentz factor. Okay, Lorentz factor gamma is equal to 1 over 1 minus u square over c square. Here u is the speed of one frame of reference relative to another, while c is the speed of light in vacuum. Okay, next snapshot is about momentum of a particle, a vector quantity. Okay, p is equal to m into v vector, where m is the particle mass and v is the particle velocity. Okay, or alternate version of this snapshot is given as p equal to mv, definition momentum of a particle. Okay, same thing, no change. Next snapshot is about relativistic momentum. Relativistic momentum, p vector is equal to m into u vector over 1 minus u square over c square. Okay, the factor in the denominator is termed as gamma factor, Lorentz factor, denoted by gamma. Okay, next kinetic energy in classical or Newtonian mechanics. Okay, the kinetic energy k of an object of mass m moving at speed v is k is equal to half mv square, where k is the kinetic energy, the energy associated with an object's motion. No vector signs, it is a scalar. Okay, m is the object's mass, v is the object's speed, it is scared, showing that direction of motion does not matter. Okay, next snapshot is about relativistic kinetic energy. Okay, the relativistic expression for the kinetic energy of a particle is k equal to mc square over 1 minus u square over c square minus mc square. This alternatively becomes equal to gamma minus 1 into mc square. Okay, gamma is the Lorentz factor. Next, there is a table of physical constants, astronomical data, in which mass of sun is given as 1.99 into 10 raised to the power 30 kilogram. Okay, this first. for the time being we are not concerned with the remaining values. Okay, we are concerned only with the first value. Okay, sun mass 1.99 into 10 raised to the power 30, radius so, orbit radius so, orbital period so, we are not concerned with the remaining parameters. Okay, now we come to its solution in a regular manner. Okay, first we find Lorentz factor gamma. Okay, gamma is equal to 1 over 1 minus u square over c square. U is given as 250 kilometer per second. We have converted kilometer into meter. Okay, so it is 25 with 4 zeros meter per second divided by, we know that speed of light is 2.998 into 10 raised to the power 8 meter per second. Sometimes we take it as 3.0 into 10 raised to the power 8 meter per second. Okay, remaining is this just simplification. Okay, simplification, no other, we will not discuss it in, because this is almost primary level mathematics. Okay, and hence our gamma factor, gamma that is Lorentz factor, becomes finally equal to 1.6 times 0 and then 35. Okay, Lorentz factor gamma has become finally equal to 1.00000036. This Lorentz factor is common for part A and part B, so properly part A begins now. Okay, part A, Newtonian momentum. Newtonian momentum, we know that Newtonian momentum is equal to mass into velocity, and mass from the astronomical data table is this 1.99 into 10 raised to the power 30 kilogram, and u, that is speed velocity, is given in the statement as 250 kilometer per second, and we have converted 250 kilometer into 25 4 times 0 meter per second. Okay, and hence after simplification our Newtonian momentum becomes equal to 4.975 into 10 raised to the power 35 kilogram meter per second. Okay, because this is 30, and from here we have taken 10 to power 5 separate and converted it in this form. Okay, now we come towards the relativistic momentum role. Relativistic momentum, dear students, we know that difference between the formula of Newtonian or classical momentum and relativistic momentum is simply that when we multiply Lorentz factor gamma with the Newtonian momentum, then it becomes relativistic momentum. Okay, so relativistic momentum is equal to Newtonian momentum into Lorentz factor, and this becomes equal to this into this. Okay, we have found Lorentz factor first of all, and we have found Newtonian momentum in the last step. Okay, so after simplification, relativistic momentum becomes equal to 4.975 0002 into 10 raised to the power into 35 kilogram meter per second. Dear students, what is the difference between this and this? Actually, this is relativist Newtonian momentum is 4.97500000000, while this has become equal to 000 into 2. Okay, very minor difference, but actually, dear students, relativity is very sensitive topic here. We have to take values after decimal to so many places. We have to use scientific calculator. We have to, otherwise we cannot express a difference. Okay, in order to make difference clear, we have to take quantity after decimal to many places in order to get the exact answer. Okay, otherwise we can say that Newtonian momentum is also 4.975 and relativistic momentum is also 4.975. Okay, if we stop to this extent, but in order to make this difference clear, we have to take the value to much accurate level, to many decimal places after. Okay, and this is what is relativity. Okay, in relativity we have to take values after decimal to sufficient length. Okay, now we come towards the question, by what factor. Okay, factor is relativistic value minus Newtonian value divided by relativistic value. Okay, so factor becomes equal to 4.0 into 10 raised to the power minus 8. We can also write it as 0.4 into 10 raised to the power minus 7, etc. Now we come towards part B. Okay, Newtonian kinetic energy is equal to half m into v square. Okay, here m is given in the table of astronomical data and v or u is given in the statement. So just simplification, it becomes equal to kilogram meter square per second square, and we know that this factor is called joule. Okay, so Newtonian kinetic energy becomes equal to 6.21875 into 10 raised to the power 40 joule. Joule, sometimes we convert joule into electron volt, million electron volt, etc. Okay, but we do not go towards those conversion factors. Okay, we stop our calculation here. Okay, now relativistic kinetic energy, formula for relativistic kinetic energy is Lorentz factor gamma minus 1 into mc square. We have found a Lorentz factor first of all in this problem, and then value of m is given from the table of astronomical data, and c, we know that c is equal to this. Sometimes we take it as 2.998 and sometimes we take it 3.0, and hence our relativistic kinetic energy finally becomes equal to 6.2685 into 10 raised to the power 40 joule. Okay, now we come towards the question, by what factor. Okay, factor becomes equal to relativistic value minus Newtonian value divided by relativistic value, and our factor becomes finally equal to 0.0079. and this is the end of our problem. This is the end of our video. Till next video, Allah Hafiz.